Okay, so today we're going to talk about the last topic in the probability unit, which is conditional probability. Before we ever get there, let's think about it using a two-way frequency table. The first table shows the number of students that passed their driving test as well as those who took driver's education class to prepare. What effect, if any, does taking the driver's education class have? Well, if we look at our table, we can see that 32 people passed who took the class, 7 people failed who took the class, 18 passed that didn't take the class, but 23 failed that didn't take the class. So out of the 80 people, 50 passed, and of those 50, 32 took the class. Out of 80 people, 30 failed, 23 of those didn't take the class. So there could be a chance that taking the course will actually help you pass the test, is what this table is showing us. So let's quickly review over a two-way frequency table just to make sure you remember what everything is and how to do it. This is the same table we had a few days ago on freshmen, sophomores, juniors, seniors, and whether they liked music, movies, or sports. This time I just added in that there's 2,500 students. So what percent preferred the music, movies, or sports? You just add up those columns. What percent of students were freshmen who preferred sports? That's a joint probability. Freshmen that preferred sports, that's 9%. How many students were seniors that preferred music? That would be the 2,500 times seniors that preferred music is 8%, so that's 225. And how many juniors were surveyed? If you add up all the juniors, you get 24% of the 2,500, which is 600 students. If you have any questions about just reading a frequency table and pulling off questions, you need to refer back to your notes from last Thursday or ask Miss Lewis. If we determine probability from a frequency table, we need to know that given a relative frequency table, which is what is above, meaning all the answers are percents, then the probability is that relative frequency. So the 9% that represents freshmen who preferred sports means that there's 9% probability of choosing a freshman who preferred sports. If you're given a regular frequency table, so just a bunch of tallies, then we need to calculate the relative frequency, which means we need to take out the frequency over the total, our traditional probability, before we can actually figure out that probability. So an example, in the relative frequency table above, what's the probability of selecting a sophomore? Well, if you add up the column or the row, there's 24 of them, 24% or 6 out of 25. A senior who prefers sports, that's in one column and row, that's 0.10, which is 10% or 1/10. Now let's look at this two-way frequency table. We want the probability of selecting a male who prefers sweet snacks. So a male that prefers sweet is 20 out of 35 because there are 35 boys. Here we're talking about males, and so that's 20 out of 35. Probability of getting a female is 28 plus 18, or 38 out of 73. Now, here's my question. Why did these denominators change? Why is this one not out of 73? This is what's considered conditional probability and what we're going to talk about a lot today. In this, it's asking you the fact that it's a man who prefers sweet snacks. So it's already claiming that they are a male. So I don't need to include these 38 people because they're no way going to be in our probability. Only these two groups will be in our probability. Whereas a female can be these two out of the entire population. It didn't refer to just salty or just sweets, just in general a female. A female who prefers salty snacks is going to be 20 out of the entire group of females, which is 38. So with conditional, you're reducing the sample space and you're calling something specific from your frequency table and then getting even more specific in your frequency table. So let's talk about the definition. Conditional probability is the probability that something happens given something else has already occurred. It's a special type of compound event. This is the notation for it, B, and then like a slash or a bar, A, and it's red. The probability of B given event A. So this is the idea that A has already happened. What's the probability that B will also happen? Conditional probability gives additional information that restricts the sample space to a smaller number of the original space. What that does is it gives us a higher probability. If we're looking at the classroom right now and we say, what's the probability that a female is wearing green? We can automatically count out all the males in the class, so by reducing our population, it gives us a higher probability of picking someone. What it does on a frequency table is it restricts it to a row or a column based off what you're given. So let's look at an example. So first we're talking about people who were polled whether they were for, against, or had no opinion about a bill to increase minimum wage. The first thing I always do with a frequency table, if my totals are not given, I go ahead and find them. So I went ahead and added up the rows and the columns for both of these to see that there's 1,000 people total that were actually polled. This table is broken down into age groups and whether they were for, against, or had no opinion. So 780 people, no matter what their age, were for the bill, and so on. 380 people were 18 to 29, and so on, being 1,000 total. So the first question asks, what's the probability that the person is 60 years old given that the person had no opinion of the bill? This idea of the word given, that they had no opinion of the bill, means I'm going to ignore everybody except for this no opinion column because I know they didn't care about the bill. So in this case, my denominator is 100. The fact that they are 60 years or older is 40. So 40 out of 100 would be my probability, which is 2 out of 5 or 40%. What's the probability that they're 30 to 45 given they were in favor of the bill? Very similar to the no opinion, we're only going to pay attention to the for column, so that's out of 780, and that they're 30 to 45 is 200 out of the 780, which reduces to 10 out of 39 or 25.64%. What about if they are against the bill, given that they are 46 to 60 years old? So here we are told a specific age group, not their opinion yet. So we're looking at this specific row of 46 to 60-year-olds, so there's 170 of them, and we want to know how many were against that bill. Well, 20 out of that 170, or 2 out of 17. Lastly, what is the probability that a person is not 19 to 29, so that's that complement, given that they are in favor of the bill? So we're only looking at the for, and we want to know the people that are not 18 to 29. So you cannot include these 310, but these three rows count. So 200, 120, and 150 is 470 out of the 780 because we know that they're in favor of the bill. So that's 47 out of 78 or 60.26%. If you have any questions on this problem, please ask Ms. Lewis now before moving on to the next one. In example 4, we're talking about Smart Block, and this is actual data the first year Smart Block was created at Rose High School. What we did was we polled 150 students 2 months after we implemented Smart Block, and then the administration made a relative frequency table based off the report card grades. So what we were doing was comparing, did they attend or not attend, and did their grade go up or not. So I left the space for you to figure out the totals. You just add the rows and columns, and then we're going to find some conditional probability. So the first question, what's the probability that a student's grade increased given that they attended an academic session? So the fact that they attended an academic session reduces my denominator to 0.66, and the fact that their grade increased is 0.48. So this problem is 0.48 over 0.66, or 8 out of 11, which is about 72.72%. Next, we are asked, a student attended academic session given their grade increase. So this one sounds very similar to A, except for if you notice, the condition is flipped. Here we're questioning, did they go to the session, but we know that their grade increased. So if I go to grade increase, that's 50%, and I'm asking, did they go to the session? So that's 0.48. So 0.48 out of 50 is 24 out of 25, which is 96%. What this tells us is of those people that their grades increase, they more than likely went to an academic session. What does that say about Smart Block? You can make any reference that you want. C, a student whose grade did not increase attended academic session. Oh, this one's tricky. You're not given the word given, so you have to play out what it's actually assuming. This word whose is another word for given. You are assuming the grade did not increase, and you're questioning, did they go to an academic session? So how many people's grades did not increase? 50%. How many of them attended academic sessions? 0.18. 0.18 out of 50 is 9 out of 25, which is 36%. What about a student whose grade did not increase, given that they did not go to the academic session? Whose grade did not increase? Whose grade did not increase? That's 50%, and did not attend is 32. So 32 out of 50 is 16 out of 25, which is 64%. It is not a coincidence that these two add up to be 100%. You are assuming the same thing for both of them, and then checking, did they go or did they not go? If there are any questions about example 4, now's the time to ask Miss Lewis. The wonderful thing about conditional probability is that you can determine independence from it. Events A and B are independent if the conditional probability A given B is the same as the probability of A occurring by itself. Conditional probability of B given A is the same if B occurs by itself, meaning the given does not affect the probability. It doesn't matter. The notation would be P of A given B is probability of A, and so on. The idea is just because we reduce the sample space doesn't change whether it's going to happen or not. So just because we're only looking at females, then that doesn't change the fact that we're trying to figure out how many people are wearing green. So here we go. Example 5. We have 110 people were surveyed about what grade they were in and whether they preferred cats or dogs. So before, go ahead and think about, do you think grade level depends on whether you have a cat or dog? You may have different opinions, but we're going to prove based off of this table whether it's independent or not. So suppose a person chosen at random from this group. Let C be the event that the student prefers cats, and T be the event that the student is in the 10th grade. So T is 10th, C is cat. So first we're going to find the probability of cat. Well, there are 22 people that own cats out of the 110. So that gives me 1/5 or 20%. The probability that a person has a cat given that they're in 10th grade, so we know that they're in 10th grade, so that's out of 20. 4 of them have cats, so 4 out of 20 is 1/5 or 20%. Are these independent? Yes. The idea, these are the same. So what that says is just because somebody's in 10th grade doesn't mean that they own a cat. Grade level and owning a cat or a dog do not affect each other. Take a moment and try the U-Trap. Pause this video before checking your answer. Okay, this one is about a group of people talking about whether they had cable or not and whether they went on vacation. So do you think having cable and going on a vacation are related? Are they independent? Well, let's see. First, it says the probability of V is that someone goes on vacation. The probability of C is that someone has cable. After you fill in your totals, you can find your probability. The probability of V is 111 out of the total 166, which is 66.87. The probability of cable given vacation is 97 out of 111, or 87.39. The probability of V given C, so that would be vacation and cable is 97 out of my cable people 135. 97 out of 135 is 71.85. And if you notice, these percentages are not the same. So are they independent? No, because they all involve money. If you can afford cable, you can probably afford to go on vacation. If not, you can't afford either.